All right, I guess we'll get started. The question is, to K8s or not to K8s, or K8s, or I still don't know how to say that. What control plane do you want to use for OpenStack? Right? That really is the question that we want to try to answer today. Oh my God, everybody's here. Sorry, did I mention that we're getting started? Okay, we're good. Yeah, very good. So, of course, the first question is, who am I and why would you listen to me ramble on about this topic for a little bit? So I founded a little technology company, Cumulus Technologies. I really sort of look at myself as a systems engineer. I look at the end-to-end solution, mostly focused on the infrastructure side of things, but understanding how applications consume the infrastructure is sort of the big question. And it's really interesting because most of the applications that we talk about, all of this open source middleware that we're using, are applications consuming and then driving our infrastructure. The technology company helps people figure out how to do that, right? That's really the point behind a lot of this. So to make this make sense, to figure out how Kubernetes may or may not make sense as an OpenStack underlay, we first need to talk about what Kubernetes is. And I'm sure many of you understand Kubernetes, but we really want to start even below that. What is a container, and why do we care about containerizing the applications, the middleware services that we're working with? So really, to me, containers break down into two different things. We talk about containers as things, because we talk about container images, right? Bundling our resources together, putting the pieces together as a single resource. And that is our software packaging model. Most application developers that you talk to, and I think many of you might even be application developers developing middleware applications, find containers to be really useful tools for packaging up their resources because they capture all the things you need to run that piece of software. So this is very powerful. So containerizing our services makes a lot of sense. In the Python space, we had something similar with virtual environments, a way to sort of say, hey, here's my Python executable, and here are all the specific libraries I need, so I'm not going to be impacted by anybody else. Containers take that a step further by also looking at things like network service, potentially storage service, and even how much of the compute resource I get. So it's not just dealing with the software components, but the whole end-to-end scenario. So we like containers because they're a software packaging technology, but they're also this next step of tying in that hardware resource as well. What am I actually consuming in these environments? Now, Kubernetes then takes the next step on top of that. So we have containers and we can run these individual processes. Kubernetes is now a management layer for managing lots of containers running. Right? And that's, I think, really important. It is another management technology. It's another piece of management middleware, which means that it's another piece that we have to think about actually running and operating just like anything else. But the basic pieces of a Kubernetes environment are sort of a control plane. So that's things like here are our API service, a controller manager that actually runs all of the logic behind the Kubernetes environment, a scheduler, something that sort of keeps track of, which button am I pushing here? A scheduler that keeps track of where resources are being placed. And then we need to also keep track of state. It's still important in any kind of middleware. And to manage state, we're using etcd, which is just a distributed key value store, but it's distributed for a reason. We'll talk about that in just a second. The other half of the service is the actual executor, the thing that's actually going to manage our containers. So we have an environment, a node, to run our containers in. So that's where we're going to actually run all of our processes. Kubernetes adds another layer. We'll talk a little bit more about this in a second, a pod. It's another way of thinking about how containers are managed. So rather than managing just a single container at a time, I might be managing a little grouping of containers. And there's all kinds of reasons why that was put in place. But when we talk about Kubernetes resources and targets, we're really talking about pods rather than individual containers and container images. In order to run those pods, there is an agent. And I'm sure anybody who's built any of the OpenStack services realizes that there are agents everywhere to actually do our bidding. In the Kubernetes space, that's the kubelet. That's the local agent that runs on the underlying operating system and then manages the deployment of our pods. There's another default agent that's pretty important in the Kubernetes space, and that's the service proxy. This is a network engagement, a network acceleration component that provides basically a load balancing across the entire set of services that you deploy. Right? And so with that, we now have a set of core resources to make up our Kubernetes system. Right? And that's most of it. The rest of the logic, the value that you get out of Kubernetes is all handled by this controller manager and it effectively telling the kubelet what to do, right? So Kubernetes, pretty simple. One of the reasons that most application developers are sort of tending towards this model is that the actual infrastructure here is pretty simple. But there's a lot more to it, and we'll sort of get into that. Now, when we look at the components of Kubernetes, like I said, pods are important because they're really groupings of containers. They're groupings of containers that allow us to be a little bit more flexible in how we think of what a container does. As I said earlier, containers are application bundles. Right? They're a way to pull all my application pieces together, but they also give me some level of inflexibility because once I've put everything into a container and I run it as a running container process, I've also restricted my visibility to all the other resources on that compute entity, on the underlying node. If I want a little bit more flexibility, the pod gives me that flexibility because it says, well, I might have containers that really do need to share resource. Maybe I have one container image that I want to use to start up my system and set up some environment for my service to run, and another one that actually runs a different set of processes, needs different libraries, so a separate container, but is really closely tied to that boot container, effectively. Well, if I put them in the same pod, now they can share a network, they can share storage resources, and even inter-process communication can happen between those containers. So it makes it just a little bit more efficient for really tightly coupled resources that I want to keep together. So pods are just a way of managing that, and the reason that there is this extra layer of abstraction in Kubernetes, and so if you start talking and working through Kubernetes, you're going to be talking about pods rather than the individual containers that they contain. Another component of containers is this concept of a deployment. Initially, there was a pod, and you would turn a pod on. You might actually have a controller like the replication controller manage those pods. Well, that's been now expanded into the deployment controller. Right? So you're actually now interacting not with individual pods, even though you still can, but you're instead interacting with deployments. And deployments keep track of state of your pods. How many do you want to have? What version should they have? Do you want to roll forward to a newer version or roll back to an older version? That's handled by the deployment and an underlying replication set that actually deals with how many do you actually want to have running. Right? So there are multiple layers here, but from an end user perspective, from a management perspective, the deployment just makes my life cycle of my individual pods easier to manage. So a pretty useful tool set. We also have this concept of a service. A service is really a discovery mechanism, but the service has effectively two views. One is, how do I find the resource that I want? Like, can I maybe have a service for Keystone, so that all of the resources that I have a way of discovering where my Keystone endpoints are? Right? So rather than having to manually define what that is, I can use something like DNS to discover what my Keystone endpoint is, and even what port I should be talking to it on. Right? So it's actually pretty useful from just a general discovery mechanism, but it also has a second resource capability, and that is that I can use a service to provide load balancing. So if the scheduler within Kubernetes goes and deploys 3 versions of Kubernetes, all equivalent, but all sort of providing my load balancing and redundancy, the service is a way to actually redirect my clients to the right running service, wherever it happens to be. So it is a redirection component, standard load balancing component that we can actually leverage as well. There are 2 other key components, and there are plenty more controllers within the Kubernetes space, but the 2 other key ones that I think are important, especially when we talk about how Kubernetes and OpenStack fit together, and that's the stateful set and the underlying persistent volume model. Now, by default, the early Kubernetes services had nothing persistent about them. The idea was that the containers were containers, they were self-contained, they might have some local storage, but if you deleted a container, anything that was stored with that would disappear. All right, so the concept behind a deployment is, hey, I can scale my web front end up and down, the web front end has no state, so I don't need to worry about anything, I can add or delete those containers at will, I can roll them forward and back at will because the state is handled somewhere else. But we know that in just about any middleware engine, I need to store state. I need to keep track of that state. And the stateful set is a way of managing order, at least. It doesn't handle every possible permutation of what your stateful service might require, but at least gives you a way of saying, hey, I know that the 3rd of my resources died, and I might want to handle that differently than if the 1st of my resources died and I want to restart that. So you have some concept of order within the stateful set. And that's also important when I then want to tie that particular state entity against persistent storage. So the persistent volume concept sort of ties into that persistent storage, that stateful set component by providing an ordered set of volumes to also work with. So I can map a volume to a particular stateful set entity and keep that ordering correct. That way I don't blow up my database by connecting to the wrong disk or connecting to a blank disk. Right? So important core pieces within the Kubernetes environment. Now, we know that in order for Kubernetes to be a good underlay for OpenStack, we need to have a resilient system. If I built a system with bare metal, I'd need basically the same set of capabilities in order to deploy OpenStack. Right? I need a model for resiliency. How am I going to handle resiliency for my control plane? Right? I need to have a load balancing service, because if I have resiliency, that usually means I have n+1 sorts of resources that are providing a particular service component. I need some way of scaling that and talking to those resources appropriately. I need a network model that makes sense. How can I access those different resources? Right? And I need distributed storage, especially if I need a stateful environment. I need a distributed storage service to support that stateful environment. And lastly, but not least, monitoring and alerting. But we can always leave that to later, right? We don't need that up front. Yeah. Somebody already has MacBook Pro local, I tell you. Yeah, I really should. Every time I do, I go back to MacBook Pro local. All right, now we've been here. Okay, resiliency. We saw this picture before. There's a reason for that. Because when I showed you this picture before, I said, oh, we got an API server, and we have a scheduler, and we have a controller, and that's all great, right? Well, we really probably want n number of API servers. If one of them dies, I want to be able to start another one, right? And actually, that API server is stateless, because the state is stored in etcd. And the way that I make this system resilient is by allowing myself to have multiple API servers. They need to be load balanced. Something has to sit in front of that to direct me to one of them, but anyone should do. My controller manager, the controller might be running some process, making a decision about where to place something, but if that one dies, another one can take over, right? Because a request was made that didn't get completed. So something has to schedule that process. It turns out that there is effectively a little bit of an engine within the API server to try to make those decisions. Hey, is there something sitting in my queue that didn't get completed? The scheduler itself is another one of these components. It's got to do some compute. It could die in the middle of the compute, but again, the API server says, well, I had scheduled a request to schedule something. If I don't get a response, I'll go ask another scheduler to take care of it for me, right? And lastly, I then need to store my state, and that's where etcd comes in. So etcd is a third-party component that's being used by the Kubernetes environment to provide a distributed key value store. And is 3 or greater, usually odd number of resources. I think actually most production-grade etcd systems, they recommend 5 etcd servers to provide your cluster. But that provides a distributed key value store. And because of the frequency of communication here, it turns out that it's an eventually consistent key value store, but that seems to work well for at least the Kubernetes environment the way it's being used. So we've covered at least the controller level resiliency. Right? There's the other side, which is then my resources. Well, if I'm deploying resources, I want to make sure that I have a resilient path to those resources as well, because I'm the control plane managing all of this. So the kubelet engine, right? If a kubelet engine dies, how do I deal with that? Well, it turns out kubelet only ever queries the API service, right? It never gets queried. So as systems are supposed to be running a certain level of state, they update their state. Kubelet tells the API service that, hey, I am running n number of these different resources. Can you tell me what you think I should be doing? All right, so there are 2 sides to that equation as well. And so with that, we now have a way of actually managing the resources as well. Service proxy I'm going to talk about next, because I have one diagram because I'm trying to keep this short enough for everybody. But we want to talk about not just resiliency, but also load balancing and the network, and I'm going the wrong direction. I think I had the same problem last time I had one of these. So load balancing service, there are a couple of different components, and if you start digging into the Kubernetes space, you'll see people talk about both a load balancer as a part of the service construct. Now, service is a discovery mechanism. Right? If I'm trying to find where a resource exists, I'll go query the service to say, hey, do you know where this particular resource exists? As a part of that, there's a load balancing schema embedded in the service that you can use. And we'll talk about that when we talk about the network, because that basically shows the network forwarding that Kubernetes overlays on top of some base resources. There's also this concept of an ingress controller, and that's really much more of an application control plane component that Kubernetes provides. It's really tied towards the HTTP, HTTPS-based load balancing mechanism that you might implement. Both the load balancing service and the ingress controller basically need something to sit behind them to provide the actual load balancing mechanism. In the service load balancer concept, usually it is a proper load balancer, either a software or hardware-based load balancing service that has a plugin that can talk to Kubernetes. Pretty powerful. If you're living in one of the public clouds, there's probably already one there available for you. If you build a Kubernetes environment and you want to make use of that resource, that's another thing you have to manage. One of the things that you might actually consider doing is running Kubernetes on top of OpenStack, because then you can make use of all the OpenStack network resources. But now we get into a whole different discussion, and we're not going to get into that today. There's also one other mechanism for providing a load balancing like resource, and that's this concept of a node port. The port part is important, because basically we're going to take the pool of ports above, by default it's 30,000 to 64,000, and we're going to use that to uniquely identify a particular application, a particular service. Right, and with that load balancing resource, I can then redirect my traffic to that particular port on any node, because all nodes are going to expose that port. All right, so it's another powerful component of the way that Kubernetes is presenting its resources onto the network. And I'm going backwards again. So the network is the other part of this load balancing story. Right? Load balancing does not exist without network connectivity. The general model for Kubernetes networks is really simple. And so for all of us that have lived in the SDN space for the last 5 to 10 years, 5, 6, 7 years, whatever it is that SDN has really become a thing, it's maybe a little bit unusual, because effectively Kubernetes tries to enable a very static model for forwarding. It does use large pools of addresses to try to do this, but basically says that at least within the Kubernetes environment, you might have to do something else to get from the outside world into the Kubernetes environment, but within the Kubernetes environment, however you want to accomplish this, I want to have L3 connectivity available between all of the pods, right? So that's that grouping of particular set of containers that were deployed. I want L3 connectivity to all those pods. Now what this means is that potentially anybody can talk to anybody else. No, there's no roles-based access, there's no security policy or anything else. By default, this is what I need. Of course, the community said, well, but I do actually want to make some restrictions, so now you can implement those restrictions, and that's actually pretty powerful, but the general precept is still there. Even though I might actually block forwarding, I at least have that one L3 model that works for everybody. Everybody can communicate. And so you see people building effectively statically routed Kubernetes environments. Any one physical node has a pool of local addresses that are forwardable. And now how do I implement that? Maybe I put a bridge down so that my containers can talk to a bridge. Maybe I just put everything onto and map everything onto a single port. There are lots of approaches. Most people actually use an SDN of some nature, right? I think the default right now is Calico. For a while it was Flannel or Weave. These things are all changing, and there's no one requirement to use one model versus another, as long as I provide L3 connectivity between all the pods. Right? Now on top of that, I may still need L2 forwarding, but that's outside of the scope of what Kubernetes cares about. Right? I might still need L2 forwarding to implement L3 connectivity everywhere. And so again, that's why we would end up using something like, and I'm sure I left somebody off. I know I left a lot of people off, but please don't think that this is saying that any one SDN is right or wrong, but here's a set of SDNs that I know have some integration into the Kubernetes space. And that's it. That's all that Kubernetes cares about for the network. So we're done. Right, we have network resiliency, except that we don't. We still need to deal with this question of how does the load balancer interact with these resources. And again, that's why I said there is, I'll figure it out at some point, really, probably at the end of the presentation I'll get going in the right direction. There is this concept of this Kubernetes proxy, and this is sort of a half-done diagram, but let's say I have 2 pods. There's a separate pod here, like here you see multiple containers. In the container networking, this pod happens to have one address. The pod has one address. The containers share that address. I'll let you figure out what the implication of that is for your containers. Don't make them both Nginx running on port 80, because that won't work. But then I have 2 more pods here, and these are the ones that I'm really kind of interested in. They're each running a single container. Oh, well, actually, there's always an extra container because there's a network container in every single pod that Kubernetes manages. But that network container basically just holds on to the network namespace and holds on to the address that's being used by that particular resource. So in the case of actually wanting to talk to one of my containers, I can potentially export a port off of this particular container right onto the physical host address. But even then, I don't do it directly. It's not that the container talks directly to the host. I still end up going through the service proxy. And the reason that I do that is that the service proxy can then redirect me to any available container. If I go talk to this particular physical address, and I don't have my container running on that address, the service proxy will redirect me to the location where it does exist. And this is why the service is such an important part of the overall Kubernetes environment. Provides me that network resiliency. If I had a connection that was going into this host 1 container and the connection dies, this container dies for some reason, or I've rescheduled it somewhere else because I'm upgrading the resource, that's okay. This proxy will now redirect any traffic that was coming to this particular node to the actual other node where that service still exists. Right? So from a resiliency perspective, Kubernetes provides a lot of mechanisms to provide application level resiliency. Right? So this is actually really powerful stuff. Now, like I said, if I want to actually do state, I do need one other component, and that is I need a distributed storage resource. There is a persistent volume mechanism. That's the terminology that's being used in Kubernetes to describe these statically configured resources. But if I can put a container on any node at any point in time, and potentially I have a separate controller that's dealing with the life cycle of those particular pods that are being deployed, then I need to have a storage mechanism that also is controllable in much the same fashion. So either I can distribute my storage everywhere, pretty commonly done with something like NFS, or I can use something like Ceph where I have a little bit more control over where that storage is actually being presented. Right? And so there are lots of drivers even here. Basically, every storage vendor in the market today has a driver that plugs into the persistent volume engine in Kubernetes. So I can use any of my enterprise or open source backed storage programs to actually tie into this, but I need to have that distributed storage. And I need that specifically if I want to use the stateful set mechanism and actually have storage associated with those containers. And lastly, let's not forget monitoring and alerting, right? Because that is an important aspect of the system. The Kubernetes community tends to like Prometheus. It's part of the Cloud Native Computing Foundation, so they all sort of play happily together. There's a lot of work that's gone into using Prometheus to manage and monitor the core Kubernetes resources. I wouldn't say that the defaults are really all that good, but they exist. And so deploying Kubernetes and having Prometheus then monitor it is a very simple, straightforward operation. That doesn't mean that you can't use the monitoring tools that you already have, and especially if you're trying to integrate this into an environment that already exists. Many people have used things like Nagios, Sensu, Zabbix, et cetera. I've seen plenty of references to all kinds of different monitoring tools being used. As long as you can monitor a containerized environment, you can use that to actually monitor what's going on within the Kubernetes environment. Right? So these are sort of the basic pieces, and that leads me to believe, at least, that Kubernetes is a reasonable underlay if I want to manage a Kubernetes environment to now run OpenStack on top of, because I have the right resources, I have the right capabilities. Now, this one I'm going to probably jump through pretty quickly, because the next question is, what if you want to use OpenStack, which I think we all do, that's why we're here. What do I need for OpenStack? Well, hey, look, I need to think about the exact same sorts of things. I need that infrastructure to be there. But from the OpenStack perspective, now I'm thinking of OpenStack as an application on top of Kubernetes. So what other things might I want to think about there? Right? What resources do I need to have? I still need resiliency. We all know that there are plenty of models, well, there's really one model for dealing with resilient OpenStack control planes, and that is the Galera cluster model for our database, because that's the thing that really is our state. So how do I deal with that? Right? We need to think about service availability. What's our monitoring strategy with OpenStack in conjunction with Kubernetes? What's our failure recovery mechanism? How are we going to deal with a failure? Does Kubernetes take care of that automatically, or do we still have to think about it, right? We still need to think about resiliency. The way that we usually do this, like I said, is twofold. One is we have a distributed database. In Kubernetes, that's etcd. In OpenStack, that's Galera on MariaDB. We need service anti-affinity, so we want to actually have some control over where our resources get placed so that we don't place all 3 of our controllers now that they're containers and potentially can go anywhere. We need to actually make sure that we actually manage that resource as well. Turns out, luckily, the Kubernetes controller can handle anti-affinity, so we can actually do that as well. And we need load balancing. We've already talked about what Kubernetes does for load balancing, and we know that that is a mechanism that we could leverage. It means that we have to manage the infrastructure for that load balancing within the Kubernetes environment, but we have a way of leveraging that directly. Now, it turns out that there's already a really good mechanism using HA proxy and keep alive D within the Kubernetes environment for managing load balancing. Turns out we can actually still use that as well, because we just treat that as an application, one of the application services that we're having Kubernetes manage for us. So at that level, resiliency, I think we can handle, right? Alerting and monitoring, this is, I think, still a big problem. Well, not a big problem, it's certainly a problem that a lot of effort has gone into trying to resolve in the OpenStack community space. I would say that there's still a lot that's needed to make for a default, simple, straightforward deployment that works. But again, the monitoring tools can make use of the Kubernetes infrastructure, can tie into, again, either a predefined Nagios environment, or potentially can start to leverage Prometheus to monitor at least the underlying resources, the Kubernetes managed resources. But I think it's also fairly straightforward to start looking at using one monitoring solution. So if you decide to go with the Kubernetes approach, why not use Prometheus to also start monitoring the OpenStack services themselves? There's plenty of work to be done there. I don't think really anybody has a single model that talks to all the OpenStack services from Prometheus, but certainly could be done. And of course, we want to be able to alert resources both from the perspective of failures, but also from the perspective of a need for scale. Because one of the things I didn't really talk about in the Kubernetes space, I guess I touched on it, this concept of a deployment being a very powerful tool really sort of extends itself even more when we start thinking about service scale. Now, usually people are trying to figure out how many Nova API services they need to run to deal with the scale of their particular consumer base. Right? How many times is that Nova API being hammered by somebody that's doing a dev test environment versus a production environment? Right? In the production environment, you would assume it's much lower than in a dev environment because you are potentially cycling resources much more rapidly. Well, can I scale my environment automatically based on monitoring and alerting coming in from the system? Maybe that's useful, maybe that isn't, but the tools are there to actually enable some of these sorts of resources a little bit differently than we might have in the past. With failures, if I have a stateless service, sort of the thing that Kubernetes was originally thought about as a tool for managing, so my APIs, sure, I can restart them anytime. I can deploy more of them, I can deploy less of them, right? I might break a connection, but our APIs have gotten smart enough and our API clients have gotten smart enough that if I lose a connection, it means that something dropped along the way, let me try again, right? So for a stateless service, it's very straightforward. For a stateless or a stateful service, on the other hand, not so straightforward. We still have the exact same problems. We have the ability to use the stateful set engine to try to make it easier to manage our Galera resource, for example. But I wouldn't say it's perfect. And I still think it's just as dangerous to turn off your entire OpenStack cluster in Kubernetes and turn it right back on without being aware of your state in the database space, even in Kubernetes. So I would say this is a problem that still has some work to be done to make it easier to manage. Although the goal of the stateful set model in Kubernetes is to help manage that class of resource. Upgrades. There is this concept of a rolling update. I think it would be really interesting to see somebody do a rolling update with Kubernetes from one version of OpenStack to another. I'm not going to claim that I'm the one who has tried this or will try it anytime in the near future, but there is the concept of upgrades. And one of the other services that helps with that is this concept of a job, because even if I do an update for something, often it's not that I just want to stop one container and start another one running. It's that I want to stop a set of containers, do something to the system, and then start another set. And the concept of a job, this is another one of the Kubernetes controllers, is there exactly to help with that. This is a single shot thing. Make sure this operation completes before you do anything else. All right? So there are ways of integrating jobs and rolling updates and upgrades as all one set of services. So again, Kubernetes could make this easier, but I think there's still a lot of work to be done in this space. So that's kind of what OpenStack needs, I think, from a control plane perspective, and hopefully you're starting to see how Kubernetes is sort of fulfilling many of these requirements. Right? So you could say, hey, this is great. Oh, well, how about my control plane? Well, here we have to start thinking a little bit bigger, right? Because Kubernetes is another tool to manage. Right? It's another set of middleware that we have to manage. So if I'm building a multi-site, multi-tenant, multi-service environment, maybe it actually makes sense to invest in running that Kubernetes cluster. Certainly a possibility. If I'm building a single-site, single-tenant environment or multi-site, single-tenant environment, I'm on the fence at this point because there is extra overhead when what I really want is a VM management system. If I want a control system for containers specifically, maybe I'll only deploy Kubernetes. Right? We really have to start thinking about what our individual applications require at that point. And if I'm doing a development environment, now I really have to ask myself, do I want to manage Kubernetes and OpenStack, or do I want to just manage OpenStack or just manage Kubernetes? Right? So I think it's important to understand what your system's requirements are. And lastly, who's supporting this? Maybe you're in a big enough company that you're just going to pay somebody to support your Kubernetes environment, in which case I would say go for it. Let them handle that layer. If you're going to then manage the OpenStack service on top, or another vendor on top of that is going to manage your OpenStack service on top, great. This might be a perfect solution for you because there is a lot of value in having these tools work together. If you're doing it yourself, do you have a team that you can actually have dedicated to understanding the Kubernetes resources? If you do, again, I think this is a great path forward, right? If you're an individual supporting the environment, now you have to understand and manage Kubernetes and OpenStack. So again, is it worth it? Depends on your actual use case, right? So if we think we do want to do this, how do I get there, right? What tools do we have available to us? And really, there are two major projects that I've seen today. There's the OpenStack Helm project. This was based on some early components. Helm, for those of you that haven't run into Helm yet or haven't run into the Kubernetes space that much yet, is yet another resource. It is not part of Kubernetes. It is a standalone product that tries to handle managing large numbers of resources, basically large numbers of pods in a Kubernetes space. How do I deal with that? How do I deal with versioning? Effectively, it's a package manager for Kubernetes as a way of thinking about it. It has some limitations in and of itself. It doesn't really have good embedded automation. It assumes that your Kubernetes environment can just run. Here are all the things that should be running. Just turn them all on. Hopefully they'll sort of sort out their order on their own. If your application does that, great. Helm's a fantastic tool because you get the right versions for everything, but it has to be sort of systems aware. And there's a lot of work in both the OpenStack Helm project and the Call of Kubernetes project to try to deal with the areas where some of that ordering is required that Helm doesn't help with. But because Helm is a very useful tool for dealing with lots of packages, and let's face it, OpenStack has lots of moving parts. All those parts have to fit together. They have to be the right versions so they can communicate appropriately. That's why Helm was chosen as a tool for helping to manage this on top of a Kubernetes environment. Now, in both cases, I still do need, at some point, an underlying image to run my service. Right? So I need a container to run, for example, the Nova API and the Nova scheduler, and all these things end up in different containers. So something has to build those images. There are a couple of different approaches that people have taken to build those individual container images. The Kala project is one that has a way of sort of building soup to nuts containers in the Docker space. The OpenStack Ansible project focused a little bit more heavily on using LXC. And one of the things that the OpenStack Helm project has tried to do as a part of their modeling was to say, well, we'll use any image. As long as you describe what that image is, whether it's LXC or Docker, we can use either of those resource spaces. I don't know how effective that is. I haven't actually done a whole lot of work myself with the OpenStack Helm project. I focused more on the Call of Kubernetes project. Not saying one's better than the other. They're just different approaches to the problem, and they might fit your particular needs more effectively. The Call of Kubernetes project, because it's part of sort of the Kala namespace, obviously heavily tongue twister this time, heavily utilizes the Kala container build process. So it's kind of focused very heavily on the Docker container space, and then builds out the Kubernetes interactions with Helm. The only other difference is that the Helm charts that are built, the OpenStack Helm project's charts tend to be system-wide. We're going to deploy Nova. and all the resources that Nova requires. The Kala Kubernetes model sort of followed along with the way that the Kala project approached images and said, well, let's keep that very fine grained. That means that we have much more control over what resources we upgrade or update in what fashion. So I don't have to update all of Nova. I can update potentially the Nova server to fix a bug, for example. That's the mindset behind those different resources. I've talked to people that have deployed with both tools and like both tools, so either one is a good resource. The other thing to think about, and this sort of goes into the set of tools, is do you have the skills? Does your team have the skills to do this? And when I look at it from the big picture perspective, we need to understand Kubernetes, how you manage services with Kubernetes, because even though these tools like Kala Kubernetes and OpenStack Helm try to manage the system for you, if you need to debug something, if you need to figure out how something's running, you need to understand how Kubernetes works. Right? So you need to have some Kubernetes knowledge, then that takes some skill development. It's all built on containers. So if you don't have container skill set, you really need to up your container skill set game as well. And again, there are multiple options. You can go the LXC route, or you can go the Docker route. I think the general application development community has gone Docker, so maybe that's just my suggestion as the direction to go if you don't have that background and want to go into this space. Understanding Helm. Helm has its own set of language components. Helm, much like Kubernetes, is based around Go and Golang instead of Python. So if you've been spending the last 5-6 years learning Python, you get to learn another programming language, which by all accounts is easy to learn, but there's more work to do. Monitoring, again, you can use your current set of monitoring tools, or you can learn another one, Prometheus, yet another way of looking at monitoring and start to integrate those sort of services and resources. And let's not forget, we still need to understand OpenStack and Python and probably Ansible, because all of the image build tools at this point seem to use Ansible as a way of generating those container images if we want to continue to support that resource. So you guys have all that down, right? Yeah, exactly. That's what I thought. So my conclusions, are you building this yourself? Do you only need VM management? Maybe stick with a containerized OpenStack. I do think containers are the right approach, maybe without Kubernetes. Right? If you're building this for production, for scale out, for dealing with multiple sites and hundreds of physical nodes, I think there's a lot of benefit to being able to integrate the Kubernetes layer. Right? Yet it's yet another layer, I agree. It's more skills that you have to learn, but I think there really is quite a bit of value in that. And there are 2 projects to help. Right? And I think the community is pushing very hard to make sure that those projects continue to be successfully supported, and hopefully eventually maybe there's 1 project to support instead of 2. But that's what we have. Right? So I think there might still be time for questions. If there are questions, I'm happy to answer questions. And if not, thank you for attending.